So in this segment, we continue with the concept of second countability for a general topological space. I'm sorry, for Rn, not a general topological space, is the Euclidean space that we were discussing about. So we continue with the second countability of that. Both the sets Q and Q plus are countable. By the way, if you have a set S and you can construct an injection from S to the set of natural numbers, you say that S is a countable set. When this injection is also a surjection, this S is countably infinite. Okay. Now, since the centers are the open balls in BRAC, which is a collection of open sets, are indexed by Q to the n. Why? Because the center is designated by n tuple. So this is the center. This is designated by Q1, Q2 all the way up to Qn, this n tuple, and each coordinate of this n tuple belongs to the set of rational numbers. So this n tuple belongs to Q to the n. Okay, which is a countable set, and the radii are indexed by Q plus positive rational numbers, also a countable set, the collection BRAC is countable. Okay, now it prompts us to define a second countable topological space. Here goes the definition. A topological space is said to be second countable if it has a countable basis. Okay. Example. Proposition 2 shows that Rn with its standard topology is second countable. Okay, now that we are familiar with the notion of second countability, it naturally arises in one's mind what first countability is. So here is the definition for first countability. Let S be a topological space P be a point in S, okay, so here is, I'm trying to draw a picture. So this is the set S, say, and P be a point in S, okay. A basis of neighborhoods at P is a collection that we are denoting by calligraphic BRAC. Okay, B alphas are elements of this calligraphic B. Of neighborhoods of P, meaning that each B alpha will be a neighborhood containing P. This is one B alpha, this is another B alpha, okay. Such that for any neighborhood U of P, okay, so we can choose an arbitrary neighborhood, okay, U of P, there is a P alpha in this collection such that this P alpha is contained in U, okay. If this is the case, then this collection is called a basis of neighborhoods at P. A topological space S is first countable if it has a countable basis of neighborhoods. It's not countable basis only, it's countable basis of neighborhoods, okay, at every point P in S, okay, which means that this collection has to be a countable collection. If this is the case, for every point P of S, then we said that this topological space S is first countable. Okay, let me give you an example. For a point in this Euclidean space Rn, let Bp1 over n be the open ball open ball with center at P and radius 1 over n in Rn. Okay, so say that this is my Rn, and I have a point P here, and say, well, so for n equal to 1, right, don't mix this n with this n, they're independent. So I think it's better to switch to some other notation here. Let us call it n. Okay. Okay, so for m equal to 1, this ball is BP1. For m equal to 2, this ball is BP1 half. There is an even smaller ball here called BP1 third. Okay. Then note that the open ball with center at P and radius 1 over m, since we have denoted with m, 1 over m, okay, in R to the n. Then this collection m equal to 1 to infinity. Okay, so you keep increasing m and you'll get smaller and smaller radius. Okay, you'll get balls of smaller and smaller radius centered at the same point P. So this collection, you have a countable collection of open balls here. Okay, so whatever neighborhood you choose around P, you can always find a ball in this countable collection that contains the point P and will be contained in that open neighborhood. Okay, so choose U neighborhood U of P. Here exists B P 1 over m. Okay, in this collection such that P is contained in BP, 1 over m, and this guy is contained in U. Alright, so this shows that, and this is the case of all P's in R to the n. Okay, it's not a compact space, it's not the correct way of denoting R to the n, but so roughly this is what we want to do, to picture as R to the n. So thus we see that R to the n is first countable. Okay, so before moving to the Hausdorff condition, a couple of remarks that I wrote under the name of an important note. The first thing to observe is that an uncountable discrete topological space is first countable but not second countable. Let me spare you a few words about this uncountable discrete topological space. Okay, so we can form a topological space, using the definition that we discussed earlier, in particular in the second segment of this lecture. But there is a particular topology that we can give to any set called the discrete topology, and that means that topology is all about declaring the open sets of your given set. Okay, so in by discrete topology we mean that the 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 collection is the topology is the collection of all possible subsets of the given set. Okay, so you remember that we discussed about this set 1 to 3, and then we can write the collection of open sets to be all possible subsets of X, which are 1, 2, 3, empty set 1, the singletons, 2, 3, then 1, 2, 2, 3, 3, 1. So there are 8 elements in this collection, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this topology of this set X is called discrete topology of X. So this is the finest possible topology that you can put on X. Okay, and so if you equip your set with this discrete topology, then the resulting topological space is called the discrete topological space. And if your this is not an uncountable set. So if your set is if your topological space is a discrete topological space like this, and at the same time if it's uncountable, then the resulting uncountable discrete topological space is first countable but not second countable. One can prove it. We're not going into the proof. I just wanted to explain this fact. Now the second important fact is as follows. One can also prove that a second countable topological space is always first countable. Okay. These were important results about first countability and second countability of a topological space. Okay, now there is an important notion called Hausdorff condition. And let me directly go to the definition. A topological space, so everything revolves around a topological space. A topological space S is Hausdorff if given any two distinct points x and y in S, there exist disjoint open sets U and V such that x is in U and y is in V. Let me draw a diagram for that. So say that this is x and there is a point y which is very close to x, okay, and we can always find disjoint open sets U and V such that U contains x and V contains y. You can always do that. So such a topological space is called Hausdorff. Okay, now there is a proposition related to Hausdorff condition. Let me state the proposition first. Proposition three. Every singleton set, by singleton set we mean one point set, okay, a one point. So every singleton set in a Hausdorff space, in a Hausdorff space is closed. So remember what closed sets are. They are the complements of the open sets. Okay. So let's prove it. Let x is an element of the set S by the Hausdorff condition for any y not equal to x, meaning that we choose any other point of the set S that is distinct from x. For such a point y and the point x, there exist an open set U containing x and an open set V containing y such that U and V are disjoint. This follows from the definition of Hausdorff condition. Okay, so which means that so let me draw the picture. So this is our set S and there are two distinct points x and y. There is an open set containing x called V. There is an open set containing x called U. Okay, and there is an open set containing Y called V. Okay. Now one has Y in V. Okay. Y is in V, right? And V is a subset of S set minus U. Okay, what is A set minus U? Let me show you. S set minus U is this shaded region, right? So we are just extracting this open set out of this set S. Okay, and then what we are left with is called S set minus U, and V is of course a subset of S set minus U as immediate from the figure. And this is happening because, so this is obvious from the picture, but this is actually happening since U and V are disjoint. Okay, this would not have happened if there was a non-empty intersection of U and V. Okay, alright, now since X is in U, or the same thing can be represented by X being the singleton set being a subset of U. Therefore, so singleton set X is a subset of U, and it's immediate that S set minus U will be a subset of S set minus X. Okay, just think in terms of the picture and you will find it right. S set minus X will be a bigger set, okay, containing S set minus U. So give it a thought using the picture, you'll be immediate. Therefore, so we have shown earlier that Y is an element of V. So we have seen that Y is an element of V, which is a subset of S set minus U, and S set minus U is a subset of S set minus singleton set X. So therefore, we have seen that given Y in S set minus X, we have chosen Y distinct from X, so that Y being in S set minus X. Okay, since Y is not the same as X, Y belongs to S set minus X. Okay, there exists an open set V such that Y is in V, and V is a subset of S set minus the singleton set X. So taking this part and this part together, we come to this conclusion, which proves that S set minus X is open. So if S set minus X is open, then of course this singleton set is closed. Okay, so this proves the proposition. So we have proved that every singleton set X in a Hausdorff space is closed. Okay, moving to an example. Okay, the Euclidean space R to the n, which is a topological space, okay, equipped with the metric topology that we discussed earlier, is Hausdorff. How do we see that? So if we choose 2 points in Rn, X and Y, okay, 2 points in Rn, then if this is the joining line between X and Y, then the claim is that so we take half of this joining line, meaning that this part, and we consider a ball centered at X and of radius half dx comma y, that we call epsilon. Okay, all right, and there is another ball centered at Y and of the same radius. This is again, this ball is of same radius, epsilon equal to half dx comma y. So it's evident from the diagram that these two balls, bx comma epsilon and by comma epsilon, are disjoint. Okay, so this topological space R to the n is Hausdorff. Okay, now moving to the concept of continuous functions. Continuous functions. Okay, let me go straight to the definitions. So first of all, we need a function between two topological spaces. Okay, so these are not merely sets. X has to be equipped with a topology, and Y also has to be equipped with the topology. Okay, so in other words, f from X to Y be a function of topological spaces. Okay, f is said to be continuous if for each open set V of Y, so let me draw a diagram again. This is say X and this is Y, and this is the function from X to Y. So we are saying that for every open set V of Y. Okay. It makes sense. We can talk about open sets in Y because Y is a topological space. So is X. We can also talk about open sets in X. So F is said to be continuous if for each open set V of Y, the inverse image of V denoted by f to the minus 1 V is an open set in X. Okay, so there is a set here corresponding to this set V called inverse image of V that has to be open in X, and only then we'll call this function f a continuous function. By the way, what is this pre-image of V or inverse image of V? This is the collection of all points X in X such that f of X, okay, is in V. This is the definition of inverse image of V, and by the definition, if this inverse image of V is open, given V is open in Y, we call that continuous we call that function between the given topological spaces a continuous function. Okay, so there is an analogous result on about continuous functions. It can also be proved. This will be immediate from what we have defined here. It can also be proved that f from the topological space X to the topological space Y will be continuous if and only if for every closed set, so instead of an open set V, we are picking up closed set B of Y, the inverse image of B will be closed in X. So instead of choosing an open set V from Y, we're choosing a closed set, a solid, a region enclosed by a solid line V, and the inverse image of B will also be closed in X. Okay, now this was just the definition of continuous, topological definition of continuous functions. Now I want to give you the definition of another concept called homeomorphism. Homeomorphism. Let again X and Y be topological spaces okay. Let f from X to Y be a bijection. Okay, we want f to be a bijection from X to Y. If both the function f and its inverse, it exists because f is a bijection, right? And the inverse function f inverse from y to x. This is a well-defined function since f is a bijection from x to y, are continuous. So what do we want? We want both f and its inverse to be continuous functions. Then f is called a homeomorphism. Okay, so let me go over it again. X and y are topological spaces, and we want this function f from x to y to be a bijection first of all, so that the inverse exists, and the inverse from y to x is a well-defined function. And now if both f and its inverse are continuous, then we say that f is a homeomorphism from the topological space X to the topological space Y. Okay, we need to give examples of homeomorphisms. Examples. Okay, the function f from R to itself given by f of x is equal to 3x plus 1 is a homeomorphism. How do we see that? Very easy. You can prove it using your knowledge in calculus, but I'm not going to go over those details of calculus, just using pictures to understand it intuitively at this moment. So let's draw the graph of this guy 3x plus 1. This is the point 0, 1, right? And there is a point here which is minus 1/3 0, and this line goes to these 2 points, right? This is f of x is equal to 3x plus 1. Okay, this is x and this is f of x. Okay. So, you know, I hope you are all familiar with the computation of inverses of such functions. There is a standard procedure of doing that. First replace f of x with y, then y is equal to 3x plus 1, then you express x in terms of y, and that can be done in the following way. 3x is equal to y minus 1, and then x is equal to 1/3 y minus 1. Then you reverse the roles of x and y so that you end up with what? Y equal to 1/3 x minus 1, and that is the inverse function of x. Since f is a bijective map from R to itself, the inverse exists, and the inverse is given by this. So this is something that you learn in pre-calculus. Okay, so now if we define, based on what we have written there, if we define g from R to R by g of y equal to 1/3 y minus 1, then it's easy to check that f of g of y is simply y, and g of f of x is s, meaning that g is indeed the inverse of f. for all real numbers x and y, okay, for all real x and for all real y. Okay, so now it's easy to see. You can see it from the picture, and if you want to go over the argument, you can also do that, also using the definition of topological, the continuity in terms of topological arguments. You can get to the conclusion that both f and g are continuous functions. How does g look like, by the way? G is a function whose graph looks like this. This is 1, 0, and you have here 0, -1/3, and this line is g of y is equal to 1/3 y minus 1. This direction is y, and this direction is g of y. Okay, so both these functions are continuous functions. So f is a homeomorphism. Okay, so there is a remark here which is important. Remark: a bijective function f from topological space x to topological space y can be continuous without being a homeomorphism. That means that f is a bijective map from x to y. So since f is bijective, f inverse exists, which is a map from y to x, right? F is continuous, but it fails to be a homeomorphism. Then what's wrong? F inverse, which is a well-defined function from y to x, is not a continuous function, and that's why it fails to be a homeomorphism. So if you have a bijective map which is continuous between two topological spaces, you cannot conclude from that it will be homeomorphism. Okay, here is an example for you. Let examples supporting the argument that we have, supporting the statement that we have given in the remark section. Okay, let S1 denote the unit circle okay, so that we can write S1 as the collection of all pairs, ordered pairs in R2, such that x squared plus y squared is equal to 1, and this set is nothing but the unit circle. And so you can think of S1 as a topological space in the subspace topology, from R2. So this is considered as a topological space so let me write it in a slightly different way. Okay, considered, so we know that, so when we are given a subset of a topological space, it becomes a topological space with respect to the subspace topology. So the subset equipped with the subspace topology is called a subspace. Okay. So S1 considered as a subspace of the plane R2. Okay. So S1, is a subset of R2, and with respect to the subspace topology, it becomes a topological space, and then therefore S1 is a subspace of the plane R2. Okay. So what I said right now, let me write it for you. Subset, if by subspace we mean it's a subset of R2 equipped with subspace topology. Subspace topology. Okay. Now I want to define a function first. Okay. Let f from 0, 1, this half open interval of R to S1 is a function between these two topological spaces. So 0, 1 is equipped with the topology, equipped with the subspace topology considered as a subset of R. Okay, 0, 1 is a subset of R. So it is equipped with the subspace topology considered as a subset of R. And S1 has the subspace topology as a subset of R2. So F can be considered as a function between two topological spaces defined by f of t is equal to cosine 2 pi t comma sine 2 pi t. Okay. This is how f is defined between two topological spaces. So now I leave it as an exercise, very important exercise for you, as an exercise for you to show that f is a bijective continuous function from 0, 1 to S1 using the properties of trigonometric functions. Using the properties, the familiar properties of trig functions. You do it. So you have to prove that f is bijective and f is continuous. Okay. Now I will show that f inverse is not continuous. Since it's bijective, f inverse exists, but f inverse is not continuous. Okay, let's do it. So the thing that we need to prove is the following. Prove that f inverse is not continuous. So let me draw the picture for you. This is 0, and I take 1/4 of this interval, which is 1/4. The reasons for choosing 1/4 I'll explain. And this function takes this 0, 1 to this unit circle in R2. Okay, this is the center, and there is this point P, which means that P is included, and I call this subset U, okay, and this arc, okay, half open arc on S1 as f of U. Okay. So first thing to note is that U defined as this 0, 1/4 is open in 0, 1. So if we dealt with such an example while we were studying subspace topology, so it's a very easy exercise to do to prove that 0, 1/4 is indeed open in 0, 1 with respect to the subspace topology induced from the real line on this interval 0, 1. Okay. Okay. In subspace topology, convince yourself. Okay. All right. So see that it's a continuous function, and I left it as an exercise, which means that f inverse exists, and f inverse is going to be a map from S to 0, 1. Okay. So in order to prove that f inverse is continuous, I have to show that an open set U here, okay, if this is my U is 0, 1/4, which is a subset of 0, 1. In particular, it's an open subset here, like we have said here. Then the inverse image of this open set in 0, 1 has to be open in S1. Okay, that's what we need to prove in order to prove that f inverse is continuous. It should be for any open set of 0, 1. But if we want to prove that f inverse is not continuous, if I can show that there exists an open set in 0, 1 for which this inverse image is not open in S1, then I'm done proving that f inverse is not a continuous function. This is exactly what we are going to do. Okay, so observe that this is nothing but fu. Okay. Okay. So there is a special point here, which is f of 0, that we are So we are defining P to be f of 0. And what is that point? See that what was f of t was cosine 2 pi t sine 2 pi t. Okay, so f of 0 is 1 comma 0. So this point is precisely 1 comma 0 on the x-axis. Okay, and this is 0 comma 1 on the y-axis. So this is what we need to show. We are going to show that fu is not open in S1. U is this open subset of 0 comma 1, and fu is this half open arc. You know, I should not say it right now. It's an arc here on S1, and we are going to prove that it's not open. Okay, let P be the point f0 like we defined here. Okay, its coordinates are 1 comma 0, and see that P is in fu, right? U is this set, U belongs to U, so of course f of 0 belongs to f of u, right? From the definition of inverse image. So in order to prove that it's open, if we want to prove that it's open, we need to find an open set in S1. Okay, so if we want to prove that this shaded arc, or this bold arc in S1 is open, we need to find an open set in S1 in subspace topology containing P equal to f0 and contained in fu. Okay, to show that fu is open in S1. This is what we need to do to prove that fu is open in S1. In other words, I need some space. In other words, using the definition of subspace topology, we have to find an open set V of R2 such that f0 is equal to P is in V intersected with S1 and is contained in f of u. I erased this picture, but we need it. Okay. this was P with coordinate 1, 0, and this arc is f of u. Okay, so we want to choose a set V of R2, okay, containing P, and that's something like this, right? And the intersection of this set, this is something like a V, okay? And if I take the intersection of this guy V with S1, I get this segment, okay? And this segment of course contains P, but no matter what I choose this V to be, I can never find a segment that is entirely contained in this arc, okay? Because this part will always remain, whatever choice I take for V, okay? Whatever open set I choose from R2 containing P, I can never confine this arc inside this regional arc, which is f of u. This will never happen. Okay, so which means that f inverse from S1 to 0, 1 can't be a continuous function between these two topological spaces. Therefore, f defined above is not a homeomorphism. QED. Well, it was not like a proposition or any theorem. It was just a statement, and this is how we prove that f defined above is not a homeomorphism. Okay. So so we are towards the end of our first lecture. I just need to say a few words about something called diffeomorphism. So we saw that when we have a bijective map between two topological spaces, we can talk about a homeomorphism, okay, for which both the function and the inverse function have to be continuous, and such a function is called a homeomorphism. But if we add more structure to this topological spaces like differentiability and so on, so that we can talk about the differentiability of function between these two spaces. This will happen for us in differential geometry when we talk about differentiable manifolds, which are more than topological manifolds. We add more structure to topological manifolds to make it differentiable manifolds. That added differentiability structure lets us talk about this function to be differentiable and the inverse being differentiable as well. Okay, and if this is the case, then if f is differentiable and the inverse is also differentiable, then we call this function a diffeomorphism. Diffeomorphism. Okay. So if you think of this function f of x equal to x cubed from R2 itself, then you will see that this f is like this, right? and it's a bijective map. Okay, and you can show that the inverse of this guy is like this, which is x to the 1 over 3. So both the function and its inverse are continuous functions. So this f is a homeomorphism, right? But the inverse is not differentiable at the point 0, so it's not a diffeomorphism, not a diffeo, although it's homeomorphism.